Hello everyone. In this video, we will learn to use bond enthalpies to estimate the enthalpy change of a reaction, to use the origin and definition of bond enthalpies to reason qualitatively about the errors in the estimates based on these quantities. In the previous videos, we learned two different methods to calculate the delta H of a reaction using tabulated values. One is by using Hess's law, and second one by using standard enthalpies of formation data. Let us say we have a hypothetical reaction. Reactants gives rise to products. Let us say we cannot express this reaction in terms of several other reactions whose enthalpy change values are known. Therefore, we cannot use Hess's law to determine the enthalpy change of this reaction. Let us also assume that we do not have the standard enthalpies of formation data for either the reactants or products of this reaction. Therefore, we cannot use the second method to determine the enthalpy change of this reaction. Now, how would you determine the enthalpy change of such reactions whose enthalpy change cannot be calculated by using Hess's law or standard enthalpies of formation data? In such cases, we use average bond enthalpies to estimate or approximately calculate the enthalpy change of the desired reaction. Note that the reaction enthalpy calculated by this method is an approximate value, and you will understand very soon why this is the case. In order to learn how to do this, let us first define what bond enthalpy is. We know that energy is released when a bond is formed and absorbed when a bond is broken. Bond enthalpy is the change in enthalpy when 1 mole of covalent bonds in a gaseous compound are broken down to form gaseous products. Let us consider the following reaction in which 1 mole of H2 gas is converted into 2 moles of H atoms in gas phase. In H2 gas, the two hydrogen atoms are connected to each other by a single bond. So, essentially, we are breaking 1 mole of HH single bond in this reaction. The enthalpy change associated for this reaction is called as bond dissociation energy or bond enthalpy. For example, the average bond dissociation energy of HH single bond is 436 kilojoules per mole of bonds. The bond enthalpy is also referred to as bond dissociation enthalpy, average bond energy, or bond strength. Basically, it tells us how strong the bond is or how much energy is stored in that bond. The higher the bond energy, the greater is the energy required to break that bond, or the greater is the energy released when that bond is formed. This is how we calculate the bond enthalpy of homodiatomic molecules. For polyatomic molecules, it would be a little bit different. For example, let us consider the following reaction in which 1 mole of methane gas is converted to 1 mole of carbon and 4 moles of hydrogen atoms in the gaseous form. The enthalpy change for this reaction is 1652 kilojoules per 1 mole of methane. If we look at the structure of methane molecule, there are 4 identical carbon-hydrogen bonds. Even though the 4 carbon-hydrogen bonds in the methane gas are identical, the amount of energy required to consecutively break each carbon-hydrogen bond varies in a non-systematic way. In this case, to break the first hydrogen off of methane, it costs 435 kilojoules per mole. To break the second carbon-hydrogen bond, it costs 453. To break the third bond, it costs 425. And to break the fourth bond, it costs 339 kilojoules per mole. The reason for this difference is that the strength of the bond depends on the molecular environment, and the molecular environment keeps changing every single time as we break a bond. Because of this reason, we use the average of these 4 bond dissociation energies to represent the bond dissociation energy of a carbon-hydrogen bond. Therefore, the average bond dissociation energy of carbon-hydrogen bond is equal to 1652 divided by 4 comes out to be 413 kilojoules per mole of CH bonds. The average carbon-hydrogen bond energies also varies from molecule to molecule as well. For example, the bond dissociation energy in this molecule is 380 kilojoules per 1 mole of bonds, and in the next molecule it is 430 kilojoules per mole of bonds. The average bond enthalpies of various types of bonds are already calculated and tabulated. For example, carbon-hydrogen bond, the average bond enthalpy is 413 kilojoules. Carbon-carbon bond is 347. Carbon double bond oxygen is 745, and so on. It is important to understand that these tabulated bond enthalpies are average values, and the true value of the bond enthalpy depends actually on the molecular environment, which varies from molecule to molecule and bond to bond within a molecule. Next, we will learn how to use these bond enthalpies to calculate the enthalpy change of a reaction. Let us say we want to calculate the enthalpy change of the following combustion reaction. Methane gas reacts with 2 oxygen gas to form 1 mole of carbon dioxide gas and 2 moles of water in the gaseous form. We are again going to use the Hess's law to estimate or approximately calculate the enthalpy change of above reaction. Let us assume a path in which all the reactants are first converted into individual atoms in the gaseous state, and then those individual atoms are combined to form products. So, let me first calculate the enthalpy cost to convert all the reactants into individual atoms in their gaseous state. To do that, we need to break all the bonds present in the reactants. There are 4 carbon-hydrogen single bonds and 2 oxygen-oxygen double bonds. Let us calculate how much energy it takes to break all these bonds. If we look at the bond enthalpies, on an average, it costs 413 kilojoules to break 1 mole of carbon-hydrogen single bonds. And we have 4 moles of carbon-hydrogen single bonds in this molecule. So, it should cost me 4 times 413 kilojoules, which is 1652 kilojoules. Next, the bond enthalpy of oxygen double bond oxygen is 495 kilojoules per 1 mole of double bonds. And we have 2 moles of oxygen-oxygen double bonds to be broken. Therefore, it costs 2 times 495 kilojoules, that is 990 kilojoules of energy. So, to convert 1 mole of methane gas and 2 moles of oxygen gas into its isolated atoms, it costs me 1652 plus 990 kilojoules, that is 2642 kilojoules. Therefore, we can say that the enthalpy of isolated atoms is greater than the reactants by 2642 kilojoules. Next, let us calculate the enthalpy change for the second step of the reaction, in which all the isolated atoms combine to form products. So if we look at the available isolated atoms, we have 1 mole of carbon atoms, 4 moles of hydrogen atoms, and 4 moles of oxygen atoms. 1 mole of carbon atoms and 2 moles of oxygen atoms combine to form 1 mole of carbon dioxide molecules. As we can see from the structure of carbon dioxide, each mole of carbon dioxide has 2 moles of carbon-oxygen double bonds. The bond enthalpy of carbon-oxygen double bond is 745 kilojoule per mole of double bonds. And we are forming 2 moles of these bonds. Therefore, the energy released will be 2 times 745, that is 1490 kilojoules. Next, 4 moles of hydrogen atoms and 2 moles of oxygen atoms combine to form 2 moles of water molecules. Let us calculate the energy released during this process. The bond enthalpy of oxygen-hydrogen single bond is 467 kilojoules per mole of single bonds. Overall, in forming 2 moles of water molecules, 4 moles of oxygen-hydrogen bonds are formed. Therefore, the energy released is 4 times 467 kilojoules, that is 1868 kilojoules. So, overall, the energy released when all the atoms are combined to form products is 1868 plus 1490, that is 3358 kilojoules. So, the overall energy of the products is lower than the energy of isolated atoms by 3358 kilojoules. The difference between the products and reactants will be 2642 minus 3358 kilojoules. If we do the math, it comes out to be minus 716 kilojoules of energy. This is the estimated enthalpy change for the combustion of methane gas estimated from bond enthalpies. In reality, the absolute value of enthalpy change for this reaction is 802.1 kilojoules per 1 mole of methane. As you can see, there is a significant difference between the enthalpy change values calculated from bond enthalpies and the true value. There are two important things to keep in mind when using the average bond enthalpies to calculate the delta H of a reaction. 1. The tabulated values of bond enthalpies are not accurate values. They are average values. Therefore, the calculated delta H of the reaction is an estimate only. It is not a true value. 2. We can only use the bond enthalpies if all the reactants and products of the reaction are gases. The reason is, by definition, bond enthalpies are given assuming both the reactants and products are in the gaseous phase.